Welcome, everybody. Today I'm going to do a presentation about using lighting for robotics applications, specifically focusing around pick and place. I'm Jack McKinley. I'm the head of the development department at TPL Vision. My main job is about looking after the product roadmap, developing new products for TPL Vision, but I also lead the trainings and technical trainings for customers and the sales team. So the presentation I have is a little bit of basics and also a little bit of sort of technical detail about how lighting works for your vision applications. So I'll just do a quick introduction. You have a camera inspecting an area that's illuminated by a light, of course. The light is captured by the camera. The camera then processes this image, and a robot is then guided to pick up the parts. So this is really the simplest setup of a pick and place system. But what we're going to focus on today is really about the lighting. So what do you want to get from the lighting? Firstly, you want to get good contrast, of course. You want to get high homogeneity. And you want to get really sharp images. And in these 3 points, I'm just going to focus everything around these 3 points. Because it seems obvious, but there's a lot of ways you can use lighting to really get the best out of your results, of course. And I'll go through a few different challenges. So you may know the word parallax. Parallax is a really common lighting problem, a really common optical problem. You would use a telecentric lens to sort of get rid of parallax problems, where you have a different optical axis. But what's lesser known is the sort of challenges that come with parallax in lighting. So when you illuminate this area here, and if you take a lux meter and you measure across your field of view, what you might see in your lux meter is that the lighting is totally uniform. So the emitted light over the area is really uniform, but that doesn't really matter to the camera. What the camera sees is more like this. So you'll see a real hot spot in the middle of the field of view. Even though you've measured it, it's really homogeneous in terms of the light output. But what the camera sees is a real hot spot in the middle of the field of view. This is caused by parallax. The reason why is due to the way that the light reflects when it hits the surface. So if you think about the light coming down parallel, you have quite a directional light, like a bar light. When your light source comes down, it will reflect off the surface. So in this example, I'm going to say something really diffused. Let's say paper or something like that. What happens is the light scatters. And the light scatters with different intensity in different directions. So if you follow the green arrow there, what it means is if you imagine that green arrow is going to the light sort of just off the center, going to the camera just off the center, and at the far side, the red arrow is going to the camera. The reflected light at the far side of the field of view is much less intense than the reflected light in the center. And this is why you see this hot spot in the center of the field of view. So you'll get images that look kind of like this. We have a solution for this at TPL Vision, where you can use angle changers and you can diffuse the light. You can create different diffusions along the length of the bar light. So you could diffuse the light in the middle to balance out this lighting effect and get a much more uniform light output. And lots of TPL Vision's customers take advantage of this to make sure that they get really uniform lighting on their field of view. They also do this on really large areas. So these are kind of simple applications. If you imagine you're inspecting a pallet or something like that, you can really play around with the different angle changers to get the best uniformity and balance of uniformity and brightness. Because that's really what it's all about. You're sacrificing some uniformity, you're sacrificing some brightness to achieve higher uniformity. And it's really about finding that balance. You can't just have really powerful lights, otherwise you'll see these hot spots. Another problem, which is a really common vision problem, is shiny surfaces. Now, if you think about the way that the light reflects when you hit something diffused, like how I showed you before, that's called your Lambertian distribution, which is the way that the light reflects off the surface. It's really hard to quantify because it really depends on the surface that you're inspecting. This is actually really the reason why all vision applications generally, you always have a lone product, you always have to test it, and it's because it's really an unknown sort of number on how much the light will reflect. However, if you look at something like this, this is a really diffuse surface. If you change that to a shiny surface, the way in which the light reflects is very different. you get a lot more intensity with the reflection, but it's a lot more directional. And in this case, when you're inspecting something shiny, you actually want to look at the light in the mirror. So you look at the reflected field of view, like that. And this is why there's general guidance that you always use a light that's double the size of the field of view. And it's due to the way that you kind of look at the light and imagine that it's a mirror. So I'd say that this is not just a sort of thing for pick and place. I would say that this is really a fundamental of machine vision to understand how the light reflects and to really see that. It's an important thing to know. Every time you pick up a light and you inspect a surface, you should always consider how exactly the light reflects off the surface. And then if you think about it, you sort of follow the photons. It's probably the easiest way to kind of figure out how to solve lighting problems. So in this example here at the bottom, it's actually the exact same lighting configuration for these 3 pictures. On the far left, you have a shiny plastic. On the middle, you have a kind of glossy rubber, which reflects the light a little bit. And on the far right, you have matte paper. Now, in all these cases, the light's the exact same. It's a flat dome, or TPL's flat dome, the HPF dome. And it's a 300 by 300 light. And you can see on the shiny surfaces, that exact width is 150 millimeters. And it doesn't matter what working distance you're at, that will always be 150 millimeters. Even if you change the optics, it doesn't really matter. The only lens which would stop that from happening would be a telecentric lens, but that's kind of impossible to place there. So a couple of examples. This example is actually just over there on the Wengler booth, but it's a pick-and-place cell, and in this case, generally with feeders, you would always use a light that's double the size of the field of view. It's not just because of the field of view that's being inspected as matte, but the parts which are in the field of view, they can also be really shiny. And since they can be anywhere there, you want to make sure that you have a light that's double the size of that working area. Now, it gets even more challenging when you start adding curved surfaces. So the shiny surfaces are always a problem in machine vision, but when you think about it, and you imagine that your camera is looking at the light in the reflection, you want to make sure that the top surface of whatever you're inspecting is filled with light, or that whatever's in the reflection of the part you're inspecting is an illuminated area, and it's illuminated really uniformly. So quite a common way that our customers get around this. It's also quite a cost-efficient way to create a big sort of field of view illumination is to use bar lights and illuminate up and create a dome effect. And this will be really uniform. It'll mean that when you have really uneven surfaces, regardless of which way they're orientated, you'll get a nice uniform surface on the top of that. Yeah. We often give the guidance that it's best that the customers, they try and point the bar lights away from the light. They don't want to have from the camera, sorry. They don't want to you want to make sure you avoid if you're using powerful direct bar lights, you want to avoid direct emission into the camera. So you just need to do some maths to kind of figure out the size of the box, the direction the light should be facing to make sure you illuminate as much of the surface as possible inside the dome, and then make sure that the camera is spaced enough back from the dome so that it doesn't capture any of the direct illumination. Another problem is motion blur. This is probably something you all know, but there's a real easy way to calculate this. And I'm sure most of you know this, but motion blur is caused when one part moves over the distance of 1 pixel during the exposure time. So the way to get rid of motion blur is to reduce your exposure time as much as possible. Now, we can do a situation where you have an example field of view 200 by 150 millimeters and a conveyor belt speed 5 meters per minute, an image resolution of 5 megapixels. You can work this out. You can actually work out your exposure time requirements from this using a really simple high school equation of the displacement over time. And you can work it out if you just make sure that you make your units in the right way. 2,000 pixels, 1,900 pixels in the direction of motion, so 150 millimeters divided by 1,900 pixels. That gives you a pixel size of 0.0789 millimeters. You know your speed in millimeters per millisecond, 5,000 millimeters per 60,000 milliseconds, and that will give you a delta t of 0.946 milliseconds. Now, to make sure you don't have any motion blur, you want to make sure you aim for at least half this value, probably a third of this value, and then when you come to do your testing with your lighting, this is your target. So you would do your testing with your lighting. At those exposure times, you would likely strobe the light and increase the brightness by using overdrive. And generally, power is always something that you want. Whenever you're using lighting, the more power you have, the more you can reduce your exposure time. You can get rid of your motion blur. You can limit the impact of ambient light. So this is the advantages of reducing exposure time. But also, you can close your aperture. So when you're on these really big fields of view, closing the aperture and increasing your depth of field, it's not just about the actual perceived distance from the camera. When you have these big fields of view, the working distance to the side of the field of view to the center can have a huge difference. So you want to make sure that you have the aperture closed as much as possible. Lastly, for pick and place, you can also use line scan systems. So line scan, generally, especially when you have these really large areas, the advantage of line scan is it can save a lot of space. And actually, it can save quite a lot of money on the lighting solution. Big flat domes generally tend to be quite complicated, especially when you need to cover an area of 2 meters wide. You can't really get them in that dimension. And line scan can save a huge amount of space by covering a really, really tiny thickness. So we've seen machines where they do pick and place systems using line scan, and they can be 2 meters wide, but the vision system can be maybe 100, 200 mil wide. So it really makes a huge difference in space and saves some money that way. The most important thing of line scan is that the light is really uniform. You want to make sure that the light is uniform and really intense. But the good thing with line scan is actually much easier to get these parameters because you can mount the light very close to the field of view. This means you can take advantage of it being a real uniform light. You don't get the effects of parallax as badly as what I was talking about in the early slides, where the reflected light can change a lot depending on where it is on the field of view. You can also use it as a backlight in the same way. It's quite clear. TPL Vision, we've got a new line scan light, which we've launched at the Vision Show this week. And it's really designed to be flexible. It's perfect for pick-and-place applications. It's got interchangeable lighting effects. So just using some simple filters, you can change this from a backlight to a focused light. And it's both based on this collimated light platform. So you start with parallel light. You can use a Fresnel lens to focus the light to get the most intensity at a close working distance. And then you can also change the filters to make it into a backlight. So it's super flexible, perfect for testing, but it's also super robust for the final application, easy to use, passive cooling, really high uniformity, and available in 8 different colors, including UV. Lastly, for robotic applications, another area people use is pick and place with the lighting on the end of arm. At TPL Vision, we have a lot of products for this. We have spotlights with zoom lenses, so you can really change and adapt it to different working distances. Also for UV, it's quite common for glow inspection. And lastly, we have a ring light, brand new ring light, which we also launched at the Vision Show this week, with a lot of really nice features. Angle changers, which is what we have for the bar lights, we now use for the ring lights. So you can really adapt your field of view on the fly using some simple accessories. We also have a really unique angle changer called the converging angle changer, where you can focus the light inward and create a really high intensity spot, which allows you to reduce your exposure time further. So just summarize. We went through some lighting issues that are caused by parallax. I would say that I put that at the start of the presentation because I would say it's one of the more useful things that not everybody really knows about. So we have a nice solution with TPL Vision, which we call the curve effect, where you can really change the lighting distribution along the length of the bar light to get the best uniformity possible. For depth of field issues, you want to make sure that you close your aperture as much as possible. So for this, you need to reduce your intensity. You need to increase the intensity of the light. Shiny surfaces, I think this is also maybe something that's useful for everybody. You have to really understand how the light reflects off the surface. Really imagine that you're following the light photons and think about what the camera sees in the reflected image. So when you're looking at shiny surfaces, actually the smaller the radius is, the harder it is to see. And that's because if you imagine you're following what the light sees in the reflection, when you have a really, really small radius, as soon as the camera looks at the part, what the camera sees goes wide. So you need to really fill the entire area with light. For motion blur, you want to use really powerful lights, specifically lights with overdrive to really flash the light with a higher intensity and allow yourself to close the aperture and reduce your exposure time. And for space constraints, we would suggest line scan systems and using the lights on the end of arm along with the camera. So thank you for listening.